Press record. Brill.
Okay.
All right. Hi, everybody. Hi to everyone watching on record. Welcome to Python Club again. If you don't already have the Colab notebook, then check out this link on the Slack channel. And if not, then just message me or Ying Ying or someone who might have a working link. The notebook's also available on our GitHub for a more or less up-to-date version. So last week and the week before, I think we were doing back to basics because it's nice to cover a few more fundamentals which come in quite useful quite often. So I thought I'd have a mix of simple but really useful techniques. So the background of the exercises was that we were following on from what we did in the basic bits Python notebook, where we translated some DNA into a protein sequence. And I've got a little bit that sort of describes the protein that we're talking about. And then in part one, we did some string processing. We copied and pasted this table as a string and did some tricks to try and extract the information from it. We worked a lot with dictionaries and dictionary loops. And then on the next session, we finished up their exercises relating to the dictionary loops and used the dictionary to find the total molecular weight of the protein. Although Steve quite rightly pointed out that we'd have to account for some water molecules that are lost when you join each amino acid. And I haven't got that left in this notebook. So in the case that you want to do that yourself, I think Wikipedia might be your first port of call. I've been throughout importing the answers from this file back to basics.py, which you can find on this link. It's got a few functions that in each step we import and then run, just in case you're having trouble getting the answers yourself. So we here import the find molecular weight, MW, for this sequence. And then we have our molecular weight calculated and printed. Looking at the number that I've printed out there is 380 something, which is worrying because it's supposed to be much larger than that. So I will try and fix that bug later on. Sorry about that. We looked a little bit about things that you can do in the Jupyter Notebook using other languages, namely Bash being a shell scripting language. That's a command line interface language. So it's orientated towards quite short but really useful commands. And because these Colab notebooks are running on a Linux server somewhere, then we can use that to call Linux commands and find out more about the computer that we're working on. We downloaded a file. It's the 3D coordinates of the protein that we saw earlier. So some years ago, someone did an experiment where they used an X-ray to find the 3D structure of this protein that we're talking about. And then we talked about using the basic Python built-in open to open the file, either in read, write, or append mode. And then extracting the data from that. And then we talked about closing the files and also the use of the context manager, which helps you handle errors and eliminates the need for you to remember to close the file manually. So is therefore sort of the recommended way of opening files like that. And then I think we got as far as looking at the contents of the file. So then we printed out a few of the lines here and there. So This is what the file looks like on the inside. So it's a text file with a particular format. And the part that we're interested in is the atomic coordinates. So each line begins with atom in all caps, and along here has the X, Y, and Z coordinates of that particular atom, and also its identity. And then throughout the rest of the file, there are other little bits and pieces of information, like what atom is connected to what. At the top of the file, there's normally some information on who did the experiment and how they did it and so on. That's called metadata. And I think maybe we got as far as talking about filtering. I'm not sure, so I'll tell you again anyway, for just in case. So the aim of that section was to go through the file object that we had here, which we now has as a list of strings, because when we read it here, we used the read lines function, which returns a list of all of the lines in the file, 9,000 lines to be precise. And now we want to filter them by lines that contain atom, like this, and then contains a sort of table-like, a table that contains the atomic coordinates and a few other things. So I thought I'd take you over the built-in filter function very briefly. The filter function is a little bit contentious. Follow this link for a little bit more detail, but there was the developers of Python for some time were considering dropping the filter function completely, because as the author of Python, whose name Guido van Rossum, if I'm saying that correctly, says that it's almost more readable to use a list comprehension with a logic statement to filter a list rather than to use this filter function. But for the sake of familiarizing you with it, I've written a very brief filter function. So the filter function takes in two arguments. It takes in a function that returns either true or false based on whether or not the item in question matches your criteria. So in this case, it will be, does this list item contain atom in all caps? And the second argument that it takes is the collection, which in our case is going to be a list, but this could also be something like a pandas series or other things like that. So initially we create a function that returns true or false if atom is in this list item, and we test it out at the bottom here on the 600th line of the PDB file. So we print it here, and we can see that it does contain atom at the beginning, and the result of the function printed below is true. So applying this in the filter context, we find ourselves with a filter object, which is what this filter function returns. And the filter function gets our filtering criteria function, that is argument number 1. Note the lack of parentheses like that. And then also the iterable, the collection, which in our case is a list that I've called PDB in all caps. So if we were to run that, and it should work if I've remembered to run all the cells, but we'll see. Okay, so see this in the top right here. That means that my runtime is only just starting. So now this is the first cell that I've run, which is why it has no idea what filtering criteria is. And it also won't have any idea what this PDB file is. So let me run all the cells. And then it will execute each cell one by one sequentially. So now we should have all of the variables that we expect here. Okay, now we're back here. So this filter function that we've called the variable as filter obj for object isn't immediately usable, but you can use it by calling the list function on it. or iterating through it in any other way. And at that point, the function, the filtering function, will actually be executed. Until then, it's, as far as I know, what's called a lazy execution, where it gets the job ready, but doesn't actually do anything until it absolutely has to. Like, for example, when we call list on it. So that's a quick example of how you might see filter in the wild. I'll skip past the output. The expected behavior is just to return a list of lines in the file that contain atom in all caps. That brings us to our first exercise. So earlier I mentioned that almost always the better way of filtering lines like this is with a for loop and an if statement. So specifically, that's referring to using a list comprehension. That is a for loop within a list, but it's just as valid to write a for loop that loops through the PDB object, does a test whether or not atom is present, and then appends it to a list outside of the loop. So your exercise is use a for loop and an if statement to extract all of the atom lines with this format. And there's an example of what one of the lines might look like. And then exercise part 2, make another to extract all of the lines that have het atom, which stands for heteroatom, which refers to any atom that's not directly part of the protein. Make another function that extracts all of the het atom lines with this format. I'm going to start a 4-minute timer. Does anyone have any questions before we start? Cool. Off you go. How's everyone getting along? Okay, I'll start to go through the answers now because I'm a little concerned that I might overrun again because I still haven't quite gauged how long each notebook takes me to go through. I think that'll just probably come with practice. has anyone got an answer that works? Okay, so one way of doing it, minus the list comprehensions that I mentioned earlier, is to do it with a simple for loop. So in this case, I create an empty list called atoms that will be ready to catch all of the list items, that is rows from the file, that meet our criteria as we loop through them. And those criteria are if atom in I, and that will return either true or false each time. And if that is true, then append that list item to this list atoms. And then at the bottom, we print it and have a look. But see how it's caught these lines near the top that we don't quite want. And notice also how it's usually atoms plural, whereas down here it's atom and then white space after that. So one way that we can refine this criteria is to find out if it's got atom space in I. Let's try that. So now the top of the list only contains three items that we don't want. So one thing we could do is make a slightly more complex rule, or the other thing is to slice it from, let's see what it looks like from the second item onwards. Well, I say second item, I actually mean the third item because of the zero indexing of Python. Looks like we need to add one more to trim off that last row from the top, atoms 3 onwards. Let's run that. Cool. How about if we look at the end of that to see if it has anything else unwanted at the end? Let me try and navigate through my notebook. Okay, here we go. So let's slice it again from -20 onwards. Let's see what that looks like. Okay, so these are the last. Where have we gone? So these are the last 20 items in that list, atoms, and they all look good enough to me. So the danger of working like this by slicing without rules is that there might well be a line in there that doesn't that isn't what I expect, and yeah, delivers me some unexpected behavior. But at the same time, it has saved me some time on making a slightly more complex rule. So from that aspect, maybe this is okay. Frankly, it all depends on what you're trying to do and how much effort you want to put into making a particular function. And in this case, from experience with this file, I know that this is an okay way of doing it.
I've got another suggestion in the comments.
Yeah, let me open that. Thanks, Steve. Checked. Might be useful to use atom starts with, yeah. Okay, so here's the code that you suggested in the comments, Steve. Atoms 1, 2, 3, 4, 5 dot starts with atom. Okay, so say I get PDB line 600, which I think I remember from earlier was a atom file, atom line. Okay, yeah, that's a more robust way of doing it. Yeah, thanks for that, Steve. So I guess in that case, the statement will be if I starts with atom, then atom append I. Let's take a look at the first 10 items in the list to see if there's any unexpected items in there. Perfect. So the starts with function, I think, applies to strings. So in this case, it does a quick logic check to see if the left side of the string, the first few letters contain this. Yeah, I guess that demonstrates another way of doing exactly that, except slightly better. Okay, I've left the answers in this back to basics file. If you're interested in taking a look at how they work, then take a look at the Python file itself. Okay.
Sorry, I have a question. So when I do it with starts with, the length of the object that I get is smaller than when I just put Atom. Am I doing it wrong?
Can you paste some code for me, please?
Yes.
Thank you. So would you mind taking us through that again? When you run starts with Atom on each item in the list, you're having a problem with length?
So I'm just saying that I get fewer lines when I do it with starts with than when I do it with just Atom. Isn't it supposed to be the same length, or am I doing it wrong?
I think the difference is probably, so let's revert back to the original one. Are you saying compared to doing it this way?
Yeah, if I just put if Atom in a line and then append it, you get fewer lines there. No, sorry, you get more lines there, and I thought they were supposed to be the same amount.
Yeah, that's a good point. Let's run that now and see what that gives us. So you're right. There are fewer lines in the method that Steve suggested, and the reason for that is that it is more effectively filtering out the items that we don't want. So in this cell, if we look at atoms, the first few are ones that we're not really interested in. And in my original answer, I went through another step to sort of trim these off. So that's the reason for the difference between these two functions.
Okay, sorry, I must have. Thank you.
That's all right. Thanks for asking. Always appreciated. Okay, let's shoot through. So the answers here extract. There we go. Extract the atoms and het atoms as a list of lists in this case. So what's it done there? Let's take a look at our list atoms. So each item in the list atoms is a single string that contains a lot of white space. But if we were to make this into a table, then this white space here is what we want to sort of separate each value by. And a simple way to do that is for each item, which will be a string, you call the string split method. And by giving it no arguments, it automatically assumes white space, although you could explicitly give it split on Fs or commas or whatever. And that's how you go from a single line string to a list. So to go from our atoms list to a list of lists that could then be put into a table, we can loop through atoms I.split for I in atoms. And there we see we have a list of lists where each sublist is a row in the table. Yeah, and then with the columns going across, if that makes sense. So that's what we've done here. We extracted that with some external functions. And now we can put this into a pandas data frame, which we've covered a little bit before, but for those who aren't in the know, it's the Excel of Python in that it's specifically for handling table-based data and has a lot of functions that you would find in Excel and more. So in this section, we're going to make data frames out of our atom and het atom data. We'll rename the columns and locate some key atoms. And eventually, we'll look at some of the lengths of the covalent and non-covalent bonds by finding the distance between different atoms based on their coordinates. So in this cell, we import pandas, an external module, as the alias PD. So earlier on in the notebook, I did also import it, which is why I've left a little comment here. But importing something more than once will kind of be ignored by the interpreter because it will detect that it already has that. To assemble these data frames from the lists of lists, it's as simple as calling pd.dataframe, the core object of pandas, around this list of lists. And from that, it will automatically divide it into a nice table. Of course, it doesn't know what we want to call our rows and columns. So we're going to have to address that very soon. We can see a set of 3 numbers that looks coordinates like, something else, and something else. If anyone knows what these numbers mean, then let us know in the comments, because that'll be interesting. Okay, there's a clue in this box for completing this exercise down here, which I haven't numbered again. I'll give us 30 seconds to solve that one real quick, and if not, I'll take us through it. Okay, anyone manage that? The answer was to call the dot shape attribute on it. So that's where the clue was hiding. So one of our data frames we've called atoms.df. Thank you, autocomplete. And if we run that in the bottom of the cell, we get this nice printout of what it might look like. If we want to find methods and properties associated with it, we can run dir for directory of it, and it will show us a lot because there's an awful lot associated with these pandas objects. But the only one that we're interested in today is dot shape, which will return the number of rows and the number of columns. So that's the answer to that one. This method also works for NumPy arrays and torch arrays, which we will come on to another time.
There's
okay,
also info. There's also info which gives you like the column names and everything and what they contain.
Okay. You know, I didn't know that one actually. That's pretty good.
Yeah.
Like that. And it tells you the D type of each one. That's useful because yeah, I was actually gonna come to that. Okay, so it tells us the name of each column, how many non-null values it contains, and then the D type, the data type of each one. Nice. All right, yeah, cheers for that, D. Okay, so let's get on to joining our 2 data frames. So you'll remember that we have 2. We have one called atoms.df and one called het.df, which contains the heteroatoms. What we want to do in this little section is to join one onto the end of the other. So the 2 tables should have the same number of columns and the same format and so on. They just contain different values. So pandas is pretty good for doing fairly complex joins, but today we'll just look at simple ones. The simplest of them being append, which you might be familiar with from the method that applies to lists. And it's designed to work in a very similar way. So we'll cover that first, and then we'll briefly look at concat, which is short for concatenate, which, similar to append, will allow you to join data frames on either axis, but offers a lot more flexibility. Okay, so here's an example of how the append function looks when you're applying it to a list. So we have a short list and we want to add an object to it. So we call the list, we refer to that, and dot append a, and then our item gets added to the end. In pandas, it's very similar. The caveat is that the data frames in question ought to be the same sort of shape. So the minimum that you can put into this command is just the data frame that you want to add onto data frame number 1. So like the list function, it gets called from the original data frame. And there are optional arguments in here as well. And by optional arguments, I mean you don't have to, if you don't explicitly type them, then they will default to these values, ignore index equals false and so on. And you can set them to true. For more information, have a little look at the pandas documentation. Here's something that I pasted from their documentation page earlier. So we have a small data frame being constructed, which looks like this: 2 columns, A and B, 2 rows, 0 and 1, and a few numerical values in there. Then we have a second data frame, which is very similar to the first, only contains different values, but contains the same column names and is the same sort of shape. Although, if we're appending onto the bottom of the table, then what's important is that the columns match rather than the rows. And we can see that when we append data frame 2 to data frame 1, we have it stitched onto the bottom. You'll notice that the index here goes 0, 1, and then 0, 1 again. So the index that we have provided won't be automatically updated unless we do some tricks. We'll come back to that later. Option number 2, slightly more flexible for joining data frames, is pd.concat. So unlike append, you don't call it directly from an object. You call pandas, which I normally import as the alias pd, and then you call the concat function, which takes in primarily a list of data frames or series, depending on what you're using. And then extra options, like, for example, the axis on which you want to join it. So, for example, if you want to join it by columns, then you might use axis equals 1, or 0 if you just want to stack it onto the bottom like that. It also has this other argument that I find I use quite a lot without necessarily understanding what I'm doing. But luckily there are few enough options for it that you can get away with a little bit of guesswork. So the outer join, which is the default, means that it will say we've got new columns in the data frame that we're trying to concatenate compared to our original. Outer means that all of the extra columns will be included in the new data frame, which normally results in quite a lot of cells that are filled with the null values. On the other hand, we can specify inner, and the only columns that will be retained will be the ones that are in both data frames. It's worth noting as well that you can have an arbitrarily long list of data frames to join, which sets it up quite nicely for, say, a list comprehension, where perhaps you could have a function that lists through CSVs in a directory and then joins them together into one single data frame, which might make it slightly easier to handle. Okay, exercise. So I mentioned that we have these two data frames, atoms.df and het.df, and we want to join them into a single data frame using both append and concat. Purely for the sake of practice is why I said to use both. And along the way, it'll be worth taking in how the syntax differs from one to the other, and then try explicitly playing with which axis you specify and playing with which type of join you specify for joining het.df and atom.df. I'm going to give us 3 minutes to do that. So primarily this exercise is becoming familiar with the concatenation and so on function. Okay, off you go. Okay, how's everyone getting along? In answer to my question earlier when I was asking about what the 2 extra columns referred to in the PDB file that comes after the XYZ coordinates, we next have the occupancy column and the temperature factor column. Occupancy, I suppose, refers to how much time the atom spends in that spot in the experiment, I imagine. But I'm treading on crystallography territory, which is something that I don't have much of a baseline in. So yeah, if anyone can shed any light on the difference between occupancy and temperature factor, then that'll be interesting to know. Okay, that's pretty much the end of that. So what I've done here is started using pandas.concat for both our data frames. And then I started playing around with different values for which axis to use and whether or not to do a join inner or outer. So the join inner or outer, when we're using an axis of 0, that is putting it onto the end, doesn't really make a difference. Or does it? 8482 rows. 8482 rows. Okay, yeah, so no real difference there. But you do get a difference when you specify as the axis is 1, where we'll be joining these side by side. Notice how the column numbers go 1, 2, 3, 4 up to 11, and then back down to 0 and up again. So that's the difference between axis equals 1 and axis equals 0. And you'll notice that when I use outer, there's a lot of NaN null values here. And you can see what's happened. The two data frames have been joined at their corner, which then leads to a lot of cells which we don't have any information for, so they're just left as NaN values. Whereas if we join it on inner, we don't quite have the same problem. Cool. Okay, well, at risk of stumbling into a topic that I don't quite know what I'm talking about again, I will carry on. This function creates a variable df, which is the data frame of both atoms with the df appended onto the bottom. And if we look at the columns, which we want to rename, it's a range object, which you might remember from other tutorials. It starts at 0, stops at 12, and increments by 1 each time. So we want to rename the columns, and the simplest way to do this is to feed or reassign this attribute df.columns as a list that must be the same length as the original df.columns. That's 12. So a list of 12 items long that will contain our new column names. So we have atom type, atom ID. I guess we can refer to the info that Steve sent through. Residue name, which corresponds to which amino acid we're talking about. The chain ID, A or B, which refers to if there's more than one protein chain in the structure, then they'll just assign it either A or B. And then we have an integer, which I presume will be the I code. Is that right, Steve?
Yeah, that's what they call it, but I'm not clear what that actually means.
Okay. Well, regardless, what we particularly want out of it is the X, Y, and Z coordinates. So as long as we have those, then we should be okay. And then I guess after X, Y, and Z, we have occupancy and temperature factor. So I'm going to replace that. Okay. So you can see how we can quite easily reassign column names to be whatever we want to. The index, that is the rows, behave fairly similarly. And in both cases, you're not limited to using just the list. You can quite easily use a whole pandas series, be it a column or a row. So in this exercise, we want to rename the rows, that is the index, based on a column in df. Which column are we going to name each row? Well, it's got to have unique items in each one. So I'm suggesting this ID column. So your exercise now will be a quick 2-minute one, or 1-minute one, let's say, to rename the index of df to be equal to these IDs. Okay, off you go. Okay, I hope everyone got on okay with that one. The answer is to call the index of the data frame. There we go, here it is. And then we reassign it as the column that we're interested in. In this case, I'm using the shortcut to look it up. That just uses square bracket slice indexing. And let's have a look at what we've done. So now the index here matches the numbers in the ID column. Bro, okay. Very quickly, I thought I'd mention our D types again as data types. So we haven't yet changed the data type of any of the values in the data frame from string to something numerical like a float. So we're going to do that now. How do I know that? Well, we have the function that Dee suggested earlier, which was df.info. Take a little look at that now. df.info. And that returns us information about each column of the data frame. And notice how under D type, it's object, object, object. Object in pandas refers to either a mixed data type or a string, usually. And I think there are maybe some other cases, some other things that it could apply to. But in this case, we're seeing object because it is a string. So if we're going to do anything vaguely numerical with it, then we need to make a quick change to the D type of those columns. Another way of finding the D type of each column is to call the attribute, sorry, the property df.dtypes. So in this case, it's not a function; it's a property of the object. So there's no need for the open and close parentheses, and we get a similar sort of thing out. So this cell really quickly loops through X, Y, and Z as strings, then locates that column, and then reassigns that column's data type as a float. So let's run that. Now if we're to run df.dtype with an S. Now we can see what we've done here. Now these are float 64s, which 64 refers to the 64-bit memory allocation. I'm not sure how to word it. But at any rate, it's a floating point number, which makes it a lot easier to work with. And I thought at this point it would be a good time to talk about NumPy, which is something I haven't actually yet covered in Python Club, despite how sort of fundamental it is in Python. NumPy is one of the core modules of Python and is primarily used for numbers in arrays and matrices and grids, and you can have arrays with as many dimensions as you want. And by that I mean you can have a 2D grid, a 1D grid, a 3D grid, or more. There's no limit to how many you use, which comes in pretty endlessly useful in scientific computing. And under the hood, it's worth knowing that Pandas also uses NumPy. It has a few abilities that improve its performance as well, relative to sort of relying purely on the built-in functions. So very, very briefly, we'll import NumPy as NP, just in case it comes in useful later. And to illustrate the point that under the hood, the Pandas data frame uses NumPy, we're going to make a new object called coords, which takes the X, Y, Z columns of the data frame, and then we extract specifically the property values, which is the underlying NumPy array that's under the hood in Pandas. So when we run that, we see it printed differently to how we used to. It's still 3 columns for X, Y, Z, and the number of rows should correspond to our starting data frame. And here we go. So just over 8,000 rows and 3 columns. The reason I bring this up is because it sort of unlocks a few more functions for us in some cases, and a lot of, well, SciPy, which we're going to come to probably in the next tutorial, is completely built on top of NumPy, or largely built on top of NumPy, which then gives us access to some pretty interesting algorithms. I suppose we'll make this the last exercise because we're coming up to the hour. So with this 3D structure that we've got, and now we have all of the X, Y, Z coordinates, we want to measure the distance between any 2 atoms in the structure, or any 2 X, Y, Z coordinates. So the equation for doing that is given here. It's a measure for Euclidean distance, which if you did Pythagoras at any point, then perhaps it will look familiar, except just plus one dimension. So in this case, this will be our first atom, its X, Y, and Z, and then its second atom with its own X, Y, and Z. And your exercise is to translate this equation into code to make a function that can find the difference between these 2 atoms. So I've already sliced them out of the coordinates frame for you, or sorry, the coordinates array. And it's worth noting that locating stuff in NumPy, you don't need to explicitly call a .locate function or anything like that. You just go straight in with the square bracket slicing. And in this case, I've got the 0th row and all the columns, and the first row and all the columns for atom 2. Okay, I will start maybe a 5-minute timer, see how you get on. Does anyone have any issues with the exercise? Issues like anything you want me to clean up? So at the bottom of the cell, I've left the function that we're working on with an input of atom 1 and atom 2, just so we can test it. At the moment, I've just got some print statements in it, but hopefully you guys will be able to fill in all the blanks. You know what, I haven't told you how to do a square root in Python. So since we've already imported NumPy, we'll use the NumPy implementation of it. np.sqrt is what we want to use. how's everyone doing with that one? Okay, so one way to have translated our equation into code would have been to unpack each individual x, y, or z coordinate from each of our inputs, which in this case I'm just labeling A and B. Let's have a look at what that returns. So let's print A within the function so that when we run this cell, it will get called on atom A and atom B. And let's also print x1, y1, and z1, which are the 3 items that we extract from this comment Albert return as well. So this is the slice of a NumPy array, which contains the 3 x, y, z coordinates of atom A. And when I print x1, y1, z1 on the next line, it prints pretty much the same thing, just as individual numbers. So I suppose that illustrates how to unpack items from an iterable. It works if the number of items that you're trying to unpack is equal to the length of the iterable that you are unpacking. So in this case, I have manually extracted x, y, z for 1 and 2. And then within this one function, I have this evaluate to this. So I tried to keep the notation more or less the same for the sake of ease. So it's the sum of the squares of the differences between the corresponding x, y, and z coordinates. All of that square rooted is equal to the distance, which then we return at the end of the function. So that's the distance here. Before we finish, I'll point out the easy way of doing it, which is to use a NumPy function called np.lineage.norm. What does that do? That finds you the Euclidean distance between 2 items. So, Steve, could you help me out on that bit? So I think I'm talking about vector norms, but I'm making a real hash of trying to explain it.
Yeah, there are several kinds of norms in mathematics, and the default one is actually equivalent to the Euclidean distance. Depends on the power that you notice this one uses squares and square roots.
Yeah.
So that means it's the Euclidean distance. If you've got different powers there, you get different kinds of distances.
Okay. So, but we're lucky enough so that in this case, this happens to be equivalent to the function that we're trying to code for.
That's right, yes.
Real.
And the main thing about NumPy is it's aware of vectors and matrices and knows how to do the mathematical manipulations efficiently.
Yeah, it does something funny with its memory allocations, right? Like it keeps
that's right, yes.
Items that are adjacent to each other in the array, adjacent to each other in memory, which makes things a little bit faster under the hood. We'll cover more NumPy in the future. I'll give a quick contents of the next lesson. So we didn't actually come on to SciPy today, but our basis will be doing lots of distant measurements. And then we'll use that to briefly look into computational complexity and how measurements like distance don't scale very well on the whole. We'll have a quick experiment that will show how the amount of time taken to calculate sort of goes up with the square of the number of atoms that you're trying to calculate for. And then we'll get into SciPy, which has some very interesting algorithms in lots of areas. But in our case, we'll be looking at the spatial algorithms and maybe talk about the installation and then dive into the algorithm itself. Okay, that's all I've got for today. Does anyone have any questions regarding any of the material that we've covered today? Additionally, so last week I mentioned software that I'm developing as part of my own work. It's enzyme or protein folding prediction and substrate docking software. And I would like some people to help me test it out and sort of, I want to gauge what features I could improve and so on. So if there's anyone interested in that, then please give me a message after and I'll talk more about it then. But otherwise, thank you everyone for coming. Enjoy the rest of the sunshine, and sorry that we're all locked down again. I'll stop the recording.